Now we are going to start with the fourth colligative property, that is the osmosis. As we have already discussed that relative lowering in vapor pressure is the colligative property, depression in freezing point is a colligative property, elevation in boiling point is a colligative, and now we have the fourth property, that is osmosis, and we are just going to prove that it is also a colligative property. So first of all, before we start with it, I want that you should know that what actually is the osmosis, right? So I'll just explain you with few examples. Suppose I have a mango, right, and I have kept this mango in a salty solution. This is my salty solution. How can you make salty solution? By adding just salt into water, right? So this is what I have done. I have added salt into water, and in that I have kept my mango. Now after after short span of time, what I get to see when I just put it inside, then it, like earlier it was like this, but after a few minutes it turned into like this. That means it actually shrivel. It actually shrivel, right? And one more example, see, I have a plant which has not been watered from last few days. That means it is in a wilted condition. As you can see that the flowers just droop, right? Now we are going to place this wilted flower into a water. That means I have a beaker in which I have a pure water, right? So when I put this flower into this, what I get to see, the flower just revived. You can see the fresh flowers again blooming, right? So that means this thing, when I kept a fresh mango in a salty solution, it just shriveled, and when I kept this wilted plant in a water, it just revived. So that means something is happening on the behalf of any movement of substance. We can say that in this something is moving out and in this something is moving in. That is why it just bloom again. So that is something called as osmosis. And as you can also see that there is a certain kind of membrane present which is just separating the two liquids. Like this is a membrane for the mango, right? This is the membrane for the plant. So likewise there is a membrane that separates two fluids actually, right? Or you can say that there is a membrane which allow the movement of substance into or inside to outside or outside to inside. As you can see that in mango something has moved out, that is why it shriveled, and in this something has moved in, that is why it bloomed again, right? So that means there occur a certain membrane, and you know that the special name for that membrane is semi-permeable membrane. Semi-permeable membrane. It is nothing, just a thin membrane, just a thin continuous membrane. But when we will visualize it microscopically, what we will get that it possesses certain kind of holes. I repeat, this semi-permeable membrane is a membrane, a thin membrane, a continuous sheet, and it contains you can say some pores, right? When we just see it with microscope, it contains certain holes in it, right? Which allow the bigger size particles to pass through, but do not allow the smaller particles to pass through. So it is in its nature actually that it will allow only selected substances to pass through. That is what is the semi-permeable membrane, right? So what do we get to see in osmosis, and or you can maybe thinking that what is the function of the semi-permeable membrane, that I am just explaining you this first, and because this is a major you can say the cause for the occurrence of osmosis. If this would have not been present, the osmosis won't have taken place. So just look at, I have an example, then we'll get into the definition of osmosis. See, what do I have in this container? I have pure solvent, as you can see with the blue circles, and here on this side I have a solution, and this is my semi-permeable membrane. You must be thinking that what material actually comprise of the semi-permeable membrane, or what you can say what substance is responsible for the selective movement of the substances, right? And you know that the semi-permeable membrane occurs synthetic in nature also, and also occur naturally. Like naturally it is the pig bladder which is used as the semi-permeable membrane, and when we talk of synthetic, the common synthetic membrane is the cellophane. You must have encountered cellophane, you can say a transparent covering that just cover the biscuits and all. So that is the cellophane membrane. So we can have the synthetic as well as the natural semi-permeable membrane. So whether it is synthetic or natural, our concern is that it will allow only selective substances to pass through. This is what we are going to see in this, right? See, this is a pure solvent and this is our solution. What happens now, this liquid is more, pure solvent molecules are more this side and less this side. So what is going to happen, this pure solvent, this semi-permeable membrane will allow only the solvent molecules to pass through. From where to where? Obviously from higher concentration to lower concentration. So this is what is happening here, that is the movement of pure solvent molecules across the semi-permeable membrane into a solution. So this is something called as osmosis. So what is osmosis? You have to keep in mind that osmosis is restricted only to the movement of solvent particles. It is restricted only to the movement of solvent particles, not of the solute, and there must possess you can say a compulsory thing, that is there should be a semi-permeable membrane. If it won't be present, then osmosis won't take place, right, because everything will just mess up then, and the osmosis is just the movement of the solvent particles. So this is what is osmosis, and after you can say a short span of time, what you will get to see that here you will be able to see the pure solvent molecules present here in the solution also. And with the passage of time, as the number of molecules of water will increase, so that means they will just increase the hydrostatic pressure also, because the hydrostatic pressure is the pressure due to water molecules. So obviously the hydrostatic pressure is going to increase, and as a result what we get to see that the level of this beaker will rise. Level of solution will rise. So if somebody is going to ask you about osmosis, you have to illustrate with an example that see, we have a pure solvent this side, we have a solution this side, and what happens, it is a natural tendency that semi-permeable membrane allow this solvent particles to move from higher concentration to lower concentration, and when they move, what we get to see that the number of water molecules just increase, the hydrostatic pressure increase, and that is why the level of the solution in this container also increase. And this actually you can say a stage comes, that is an equilibrium is reached when the molecules on both the sides just become equal. Right, so this is what is osmosis. Now what will happen with the passage of time, just we are going to start with a new term, that is the osmotic pressure. Just look in this figure. It is just similar to that, but just to explain osmotic pressure, I am just considering a different figure. So what is going to happen? Again, we have a solvent, we have semi-permeable membrane, we have a solution. As you know that solvent particles are more this side and less this side, so that means they will move this side. Right, and with the passage of time, I told you that as the number of water molecules will increase, so that means hydrostatic pressure will increase, the level will increase, and what you will get to see that this the piston of this side will start moving upwards. So let's say that it will move from this place to this place, right. So that means osmosis is just increasing the level of the solution in on the one side where the solvent particles are carried, right. So this is what we get to see. Now if I apply an external pressure from this side, if I apply external pressure from outside, what is going to happen? Like if I apply pressure and I am just going to move the piston down, then what is going to happen? Obviously what is going to happen? These solvent particles will be you can say that like again I am telling you, see if we apply pressure, it won't allow the more solvent particles to move from this side to this side. So that means the osmosis will cease now. That is something called as osmotic pressure. So what is osmotic pressure? It is the extra pressure which is exerted from outside obviously to stop osmosis, and a stage will come when the osmosis will just cease. That means the more solvent particles won't move from this side to this side. And you know that if you apply this pressure more than the you can say a limit, then what is going to happen? It will also like when I apply, suppose I say I apply pressure P, right. So when I apply pressure P, so this much pressure is sufficient to stop osmosis. But suppose I increase this pressure from P to P dash, then what is going to happen? It will just reverse the osmosis process. That means it will now push these solvent particles back into the pure solvent side. So that is something called as reverse osmosis. Even reverse osmosis plays an important role, like desalinization of seawater is an application of reverse osmosis. There what we do, we apply a certain pressure more than the limit, then what we get to see that the solvent particles just move from the solution back into the pure solvent. So we can have the reverse osmosis also. But for that what is needed? Obviously a pressure is needed, and that pressure should be more than a certain limit, right? Then only, because see, when the pressure is equal to the hydrostatic pressure, it is just called as osmotic pressure. It will just stop the osmosis. But if that pressure is more enough, then it can even force the solvent particles to move from this side back to this side. So this is something called as the reverse osmosis, used for the desalinization of seawater. Now, as you all know that this is the osmosis, then what we get to see that osmotic pressure, we see that osmotic pressure is directly proportional to the concentration of the solute. And we know that any property which is directly proportional to the concentration of solute is nothing but a colligative property. This is what we wish to prove, right? We are studying this process because we want to prove osmosis as a colligative property, and hence we have reached the conclusion that this osmotic pressure is obviously directly proportional to the nature of the the number of the solute particles. This is what we get to see here, because osmotic pressure which will be applying from outside at least should be equal to that it should be enough to move the solvent particles back, whether we are talking of reverse osmosis or whether we are just talking to stop the osmosis, right? So this is what is going to happen here. So what we have reached the conclusion that the osmotic pressure is directly proportional to the concentration. Here the concentration is not molality, keep in mind, because earlier when we proved depression in freezing point as colligative property, or elevation in freezing point, the boiling point as colligative property, there we took concentration in terms of molality, right? That is number of moles present per kg of solvent. But here what we have molarity, that is the number of moles upon volume, that is in liter. And moreover, when we remove proportionality sign, we put constant, and this is nothing but RT. R is a gas constant and T is definitely a temperature. So this is what we get to see, that the osmotic pressure is equal to N upon V RT. So this is the expression, if you wish to, like if you get a question something like that in which you are given with the gas constant, you are given with the temperature, you are given with the moles and volume, and you need to calculate the osmotic pressure, then you can calculate by this formula. And hence we have reached the conclusion that it is definitely a colligative property, because it depends upon the number of the solute particles independent of the nature, right? It is independent whether it is an NaCl, Ki, urea, it has nothing to do with the nature. It is just concerned with the number of the solute particles and likewise the binding force. So this is what it is, a colligative property. Now, if we wish to calculate molar mass due to osmosis, then how we can do that? As we know that pi is equal to number of moles divided by volume RT. So we know that we can write number of moles in terms of solute, that is the weight of solute divided by molecular mass of solute. So this is what we are going to put here. So what we get after putting this, so we can just shuffle them up and we can calculate the molar mass of the solute. So as we have just done with the osmosis, I just want to make you familiar with the types of solutions that we, like, depending upon the concentration of solute, we divide solution into three types. Depending upon the concentration of the solute, that how much solute is present, we divide the solution into three categories. One is the hypotonic solution. So let us say this is hypotonic, other is the hypertonic, and the other one is isotonic. It is just depending upon the number of the solute particles present. So what you get to see in hypotonic? So let us say that it is hypertonic, because I have already made the figures, so it will be convenient for me to explain you. So let us see that it is hypertonic and this is hypotonic. Hypertonic solution is nothing but a solution in which the solute content is more and comparatively water or a solvent content is less. I repeat, hypertonic means solute is more and comparatively water is less. That means it is a concentrated one, not a dilute one. But in hypotonic, what we get to see, that solute is less and water or a solvent is more in quantity. And in isotonic, what we get to see, that the concentration of solute and solvents are almost same. Now what I am going to do, I am just going to explain you that what happens when we keep certain cell like egg or mango or RBC or any other thing, when we keep in these three kind of solution, we get to see different kind of changes. So let us take RBC, that is our red blood cell, which is present in the blood, you know that, which is responsible for the transportation of gases, that is, as it contains the red color pigment hemoglobin made up of a heme protein, you know that. So what I am going to do, I am just going to place that RBC in different types of solution, and I am just going to observe the changes that are occurring, taking place. So in here what I have done, I have just placed the RBC in hypertonic solution. So hypertonic is that in which the solute concentration is more and obviously the water concentration is less. And as we know that the water particles just move from their higher concentration to lower concentration. So that means in this case RBC will have more content of water as compared to the solution because it is hypertonic. So that means water will move from higher concentration to lower concentration, and this will be a semi-permeable membrane. So what will happen? The water will start moving out, and as a result what we get to see that it will become shrivel, it will shrink, and finally when it becomes, when finally a limit is reached beyond that which it cannot shrink, that stage is called as flaccid. So what we observe in this, when we kept RBC in hypertonic solution, water being more in RBC as compared to the hypertonic, so water moves from the RBC into the solution. That is what kind of osmosis is taking place? Obviously exosmosis. That means the movement of water from the cell into the solution, right? And what we get to see, what result, what observation do we get to see with passage of time? We see that it will start shrinking, and when a level is reached that beyond that it cannot shrink more, that condition is something called as flaccid. So that means whenever you will keep cell in hypertonic solution, ultimately it is going to turn into a flaccid type, right? That means it will fully get shrinked. Now we have hypotonic solution. Hypo is that in which the solution is less but the water is more. Obviously it is a dilute solution. So that means if we compare water content of cell and solution, obviously it is going to be more in solution. So that means water will move from the solution into the cell. That is what kind of osmosis? Endosmosis. That is movement into the cell. Then what happens? A cell will start swelling up. Cell will start swelling up because water is moving in, and the stage is reached that beyond that it cannot, you can say, it cannot experience much hydrostatic pressure, and that fully swelled stage is called as turgid. So that means whenever the cell is kept in hypertonic solution, what kind of osmosis is taking place? Obviously endosmosis will take place, and as a result it will swell, and finally a limit is reached, which is when it turns into a turgid cell. And when we keep in an isotonic solution, nothing happens, because actually the concentration of solute and solvent is same in both the cases. So that means cell will remain same as such. See, I have drawn figures for you. This is my RBC before keeping in a hypertonic solution, and after that what happened, that it just got shrink, and this is my flaccid cell. And when I kept in hypotonic, it was my original cell, and after just absorbing the water it becomes swell, and this is my swelled cell, that is my turgid cell. And when I kept in isotonic, it remains same, because water moved neither from the cell to the solution nor from the solution to the cell. So that means it is kept as it is, it remains same. This is what we have. A few more terms I have for you, that is a process of plasmolysis and deplasmolysis. See, we observe this plasmolysis and deplasmolysis in case of plants. It is generally observed. So what happens? Suppose I say that for few days you just forgot to water your plants, right? For few days you just forgot to water your plants. So what changes will you observe? Leaves will droop, obviously the flowers will start shrinking, and or you can say your flower will become just like that. It is a wilted condition, right? Now suppose I am going to keep it in a hypertonic, or we'll start with another example. Just listen to me. See, we have a plant, a fully grown plant, a fully plant which is fully turgid, fully fresh plant. When we kept in this hypertonic, so obviously it just shrink, and ultimately it is called as plasmolized cell, or a plasmolized plant, we can say, because all the water just moved out, and as a result it just wilted. right? And you know, there is a certain stage that like if you stop watering your plants, there is a certain stage reached, like before that if you water them they can just revive again, but if they just go through that phase they won't revive. How much water you add doesn't affect their growth, right? So that means if we have a cell which is just shrinked, which is in a you can say in a period of time where when you can water and make them that fresh again, so that is called as plasmolyzed plant or a cell. And now when I am just going to remove this plasmolyzed cell from here and I am just keeping in a hypotonic, then what will happen? Here exosmosis take place, here the endosmosis will take place, and all the plants and the flowers or the leaves, it will revive again and it will again become healthy one. So this is something called as plasmolysis and deplasmolysis. So what is plasmolysis? When you keep the cell in hypertonic solution, it becomes flaccid, and when in a you can say a short span of time you transfer into a hypotonic, again the endosmosis take place and it again becomes turgid. So this is what is the plasmolysis and the deplasmolysis. So hence we have just reached to the conclusion that osmosis is definitely a colligative property. It depends upon the number of solute particles and independent of their identity. So we have already proved all four properties as a colligative property. Now we'll start with another topic, that is the abnormal masses.